Virtual machine sizes play a central role in ensuring that workloads run efficiently in Azure environments. Building on previous exploration of resource templates and disk encryption, effective VM sizing addresses performance, cost, and reliability requirements. By selecting suitable CPU, memory, and storage configurations, organizations can optimize virtualized workloads for various use cases. Incorrect sizing can lead to wasted resources or system bottlenecks. So an in-depth understanding of size offerings and how to adjust them is essential. These principles enable administrators to scale applications up or down in alignment with evolving business demands and budget constraints. Azure offers distinct virtual machine size families tailored to diverse workloads. General-purpose sizes, such as the D-series, balance CPU and memory for common business needs. Compute-optimized sizes, including the F-series, deliver a higher CPU-to-memory ratio for tasks requiring intense processing. Memory-optimized variants, such as the E and M series, handle large database or analytics workloads. Storage-optimized configurations, like L-series, cater to applications needing rapid input-output operations. Finally, GPU-enabled sizes support graphics-heavy or machine learning tasks. Familiarity with these categories allows administrators to align each workload with an appropriate subset of Azure's VM size offerings. Selecting an appropriate VM size depends on workload patterns, performance targets, and budget constraints. Administrators should gather CPU utilization, memory usage, and storage IOPS metrics to identify optimal configurations. A test environment can help validate performance under real application conditions before deployment. When working with resource templates, including Bicep or ARM, these metrics guide parameter values that reflect operational requirements. Oversizing can lead to unnecessary costs, whereas undersizing might undermine performance. Continuous monitoring ensures that chosen configurations remain effective as workloads fluctuate or new features emerge, maintaining adequate capacity without excessive resource consumption. Azure's web portal enables administrators to resize existing virtual machines with minimal disruption. By stopping the target VM, users can navigate to the size blade to select an alternative configuration. The interface displays cost estimates, core counts, and memory allocations to facilitate informed decisions. Once the VM is reprovisioned with a new size, any attached disks remain linked. However, certain size transitions might be restricted by regional availability or hardware limitations. Administrators should confirm that the desired size is supported in the VM's current region or consider relocating resources, if necessary, to ensure compatibility. The Azure Command Line Interface, CLI, offers a scriptable method for adjusting VM sizes. Administrators often stop the VM, then run the following commands. Bash AZ-VM deallocate. Resource group RGName. Name VM name AZ-VM resize. Resource group RGName. Name VM name. Size standard underscore D2S underscore V3 AZ-VM start. Resource group RGName. Name VM name. This approach is beneficial in large-scale settings where programmatic automation reduces repetitive tasks. By combining CLI commands with shell scripting or CI/CD pipelines, organizations gain a quick and reliable way to enforce consistent sizing across multiple VMs without repeatedly using the portal interface. PowerShell provides an alternative automation route for resizing Azure virtual machines. Required modules allow administrators to authenticate and control Azure resources. A typical sequence includes stopping the VM, resizing, and restarting. PowerShell stop as a VM. Resource group name RGName. Name VM name set as a VM size. Resource group name RGName. Name VM name. VMSI standard underscore D2S underscore V3 start as a VM. Resource group name RGName. Name VM name operating within Windows-based environments. These commands can be integrated into broader scripts or scheduled routines. Administrators can then uniformly apply size adjustments across critical infrastructure, ensuring consistent performance and provisioning within organizational policies. Azure Resource Manager templates define deployments in a declarative format. By specifying the VM size property within the virtual machine resource, administrators ensure that newly created or existing VM instances adopt uniform configurations. Parameters or variables allow for environment-specific sizing, so production and testing can share a single template structure. Once the template is updated, redeployment applies the new VM size. This method embodies infrastructure as code principles by maintaining version definitions. Changes to size values become transparent, promoting review processes and alignment with best practices for repeatable and auditable infrastructure management. Bicep is a domain-specific language that simplifies ARM template authoring. Administrators can specify VM size within the virtual machine resource, optionally using parameters to set the size at deployment. By reducing syntax complexity, Bicep helps teams avoid mistakes and accelerate the rollout of updated configurations. This model remains compatible with Azure Resource Manager, ensuring all features are available. Storing these definitions in source control establishes a reliable system for tracking changes. As workloads grow or shrink, updating the Bicep file to adjust the VM size parameter promotes transparent, consistent, and efficient reconfigurations aligned with operational demands. VM size directly influences Azure billing and application performance. More powerful sizes can handle heavy workloads but result in higher monthly costs. Conversely, smaller machines lower expenses yet may cause performance bottlenecks under peak traffic. Administrators should interpret usage metrics from Azure Monitor, including CPU and memory utilization, to determine the financial impact and potential resource saturation. Periodic reviews ensure that the selected size remains appropriate as workloads evolve. Adjustments, either upsizing or downsizing, enable an organization to align capacity with operational objectives, managing real-time traffic demands without incurring wasteful overspending or heightened risk of outages. Scaling strategies in Azure involve either horizontal or vertical adjustments to accommodate shifting resource requirements. Horizontal scaling, often implemented through virtual machine scale sets, adds or removes instances based on metrics like CPU usage. Vertical scaling, by contrast, replaces the existing size with a larger or smaller option, which can be effective for workloads that cannot be distributed across multiple machines. Each approach must be balanced against factors like availability, cost, and the nature of the application's architecture. Identifying the optimal strategy promotes effective resource usage, especially in dynamic environments with unpredictable or fluctuating traffic demands. Certain VM sizes offer specialized storage or networking features vital for performance-sensitive workloads. For example, high-performance VMs might support premium SSDs or ultra-disks to handle high I/O. Some memory-intensive machines can utilize accelerated networking, reducing latency in data transfer. Administrators should confirm that a VM's selected size aligns with the required disk type or network capabilities. In specialized scenarios, such as high-performance computing, RDMA technology may be a critical factor. Evaluating how CPU, memory, storage, and network components interact ensures a balanced environment that avoids bottlenecks and maximizes concurrent access to shared resources. Active monitoring of VM resources helps administrators maintain optimal sizing as workloads shift. Metrics such as CPU usage, memory consumption, and network throughput indicate whether a VM is operating within acceptable thresholds. If repeated spikes surpass a safe margin, resizing or adding additional instances can preserve responsiveness. Conversely, consistently low usage suggests a smaller size could reduce operational expenses. Azure Monitor and Log Analytics capture historical trends that highlight usage patterns over time. Administrators can then plan system changes that align capacity with evolving demands, ensuring uninterrupted services without incurring unnecessary costs or resource shortfalls. Effective VM sizing combines data analysis, cost control, and operational foresight. Administrators should base their choices on real usage metrics from test or pilot environments before rolling out to production. Integrating resource definitions into ARM templates or bicep files ensures consistency across deployments. Regular reviews of system performance guide potential updates, such as switching to a more powerful size or downsizing to a lower tier. By leveraging Azure's built-in monitoring tools and automated scaling options, organizations can proactively respond to workload demands. This approach minimizes overhead while maintaining stable performance, benefiting both technical efficiency and budget alignment.